Okay, hello everyone. So I'll just start explaining the two problems now. So uh for the first problem we have a bully like this, and there's a mass here, M1, and another mass here, M2, which has water leaking out of it at a constant rate dm over dt is equal to r0, and the water leaks out with a velocity v0 relative to the container. And so we want to find the acceleration of m1 as a function of time. Okay, so basically, if we know that the acceleration from we know that the force from gravity is just mg. So there is this gravitational force, and that's m1g, and then there's also this force, which is m2g. But if we want to find the acceleration of m1, we have to subtract this, because if you think about it, the gravity is pulling the m2 the other way. And so finally, there is a force from that comes from the water leaking out. So to find this, we can basically look at it in this way. The force F is dp over dt. P is the momentum. This is dmv over dt. And this is equal to dm over dt times v plus dv over dt times m. So this second part is just ma, and we already found that part, so we don't need to worry about it for now. But to find dm over dt times v, we can do it in this manner. So suppose we have suppose that the velocity of the system is, suppose the velocity of the mass m2 is v at some point, at this point. So then we can use conservation of momentum this way. So the momentum is, of course, m2 times v. And then this has to be equal to the momentum of the mass after it has to be equal to the sum of the momentums from the water leaking out and the mass moving up afterwards. So then if the mass of the water leaking out is delta m, then the velocity of this water is v minus v0, because v0 is the velocity of the water relative to the container. So then this added to the mass of the mass of m2, which is just m2 minus m0 now, multiplied by v plus delta v. And delta v, this is the new velocity because it's changed after the mass is changed. And so then we can we get that this is equal to delta mv minus delta mv0 plus m2v plus m2 times delta v minus delta mv minus delta delta v. And so this last delta m times delta v is really, really small. So we can basically just ignore it. So then now some of these terms will cancel out, and this m2v and m2v cancels out. So then we get that m2 times delta v is equal to delta m times v0. Okay, so now if we divide both sides by delta t, then we get that Yeah, so then we get M2 times delta E over delta T is just equal to R0 times V0. Okay, so then that means that basically there is also these basically there this since this M2 times delta V over delta T, that's just like the force. That means there is this extra force coming from the water flowing out. And so it would be, well, and in this case, it would be opposite to the force, the gravitational force on M2 because it's getting smaller. Because so basically the water flowing out causes creates a force that goes upwards. So then in this case, let me see. So then our equation now becomes m1g minus m2g plus r0 times e0, which is the force that we just found. So then now all we have to do is take this over the total mass of the system. And so m2, we want to find this as a function of time. M2 is just equal to m0 minus m0 minus r0 times t. So then the total force would just be so then it would just be m1g plus r0 b0 minus this over the total mass, which is of course plus m0 minus r0 t. So yeah, if you can write this in a number of different ways, but basically this is just the answer to the first problem. Okay, so then for the second problem, we have these two containers who have, well, both of them have the same volume V, and so these are the respective pressures and temperatures P1, T1, P2, and T2. And so we want to find the final pressures and temperatures after the valve is open so that they form one big container. Okay, so basically to solve this, we just use something called the ideal gas law, which is that the pressure times the volume is equal to nRT. So then we have P1 times V is equal to N1 times R times T1. R is a constant, and N1 is just the amount of gas in moles. Similarly, P2 times V is equal to N2R T2. So then we get these expressions for the values of N, P1V over RT1, and N2 is equal to P2V over RT2. Okay, so then now to solve for the temperature first, we have we can use the we can just use conservation of energy. In this case, the energy can be given by this formula. F U is equal to F over 2. F is the number of degrees of freedom, which I'm not going to get into here, but you can like look that up yourself. Yeah, times nRT. So then we have that from conservation of energy, we have that F over 2 times N1 R times T1. This is the initial energy of this first container plus F over 2 times N2 RP2 is equal to the final energy, which is of course F times N1 plus N2 times R times final. This is because like it should be fairly obvious why the final, well, we have N1 plus N2 in the final on the right-hand side. It's because like you just add the amount of gas together in the final container. So now we can just cancel out a bunch of stuff. These all get canceled. And so then we get TF is equal to N1 T1 plus N2 T2 over N1 plus N2. And so then now we can just plug in our expressions for N1 and N2, and we get, this gives us P1 plus P2 over P1 T2 plus P2 T1 times T1 T2 in the end. Like you can just plug in the expressions to find this. And then to solve for the pressure, let's see. Okay, to solve for the pressure, remember how I said that the energy is F over 2 times nRT? Well, if you look back at the ideal gas law, nRT is just equal to PV. That's just another way of writing the energy. And so then we can just apply it again. F over 2 times P1 V1. Oh, well, it's just V plus F over 2 times P2 V is equal to F over 2 times P F times 2V. This is because in the end, the volume is just 2V. So then this is fairly straightforward to solve. We can just cancel out all this and we get P of F equals P1 plus P2 over 2, which is a pretty nice answer. So yeah, that's the answer to the second problem. Does anyone have any questions? Okay, if no one has any questions, then that's it for me.